All right, and we're live. So it's been a very long time since I've used my Twitch account, but you know what? Here in good old 2021, I figure it's about time to brush the dust off and give things another shot. So I'm gonna go ahead and before we really get rolling here, I'm gonna go ahead and make sure we get the good word out. All this stuff is starting. So let me go home real fast. I'm going to go ahead and put some of the stuff out there. Let's see. That should be me right there. Perfect. All right. And before we really get rolling, I'm going to go ahead and just double check our audio. All right. All right. All right, there we go. Went ahead, got everything up on social media. Gonna go ahead and signal boost that a little bit, and we'll go ahead and just get right into it. Okay. Now, so in terms of what we're actually going to be covering today, and what we're going to be taking a look at, all about basically learning how to go ahead and improve .NET data structure performance using benchmark.NET and .NET 5 behind the scenes. And we'll also be using a little bit of .NET Core 3.1 as well. Now, when do you actually want to go ahead and benchmark something? Well, you only really want to benchmark something if you have some of the following conditions appear. First is, if you're interested in benchmarking your CPU utilization or your throughput, you're going to want to go ahead and take a look at code that is being frequently called on a hot path inside your application. So if you're building a web application, this might be all the code that sits in the middle of your HTTP processing pipeline. That'd be a place you might want to go ahead and look. If you have code that has visible performance issues in important edge cases, it's a good example. If you have a data structure that is implemented as a collection and that data structure starts to have some performance issues once it reaches a very large size, that's something you're probably going to want to benchmark and take a look at, because the performance characteristics of that data structure might be very easy to miss when it doesn't have a lot of items in it. Or maybe you have an issue with, let's say, the types of content that are in your data collection. So if your data structure starts having, let's say, all sorts of different tuples of different values show up, this might be something that becomes a problem a little bit further down the road. Finally, you also want to take a look at memory consumption when you're benchmarking as well. So you might want to take a look at code that allocates a large amount of process memory, so meaning that these objects are taking up a lot of the finite resources your machine has. And if these objects get too large, you might end up having problems basically related to total memory consumption inside the system. I'm just going to turn the Twitch music down a little bit. There we go. So you might end up having some problems with the total amount of code, the total amount of memory that's being consumed behind the scenes. Finally, the last thing we want to take a look at for doing benchmarking is code that allocates and gets garbage collected frequently. This not only creates memory pressure inside your system, but it also contributes to decreases in CPU, because the garbage collector requires a reasonably large amount of resources to run behind the scenes. But beyond that, it's also responsible for creating memory fragmentation and other facets of your application that might have a visible impact on performance. Now, what we're going to go ahead and take a look at is an issue that I think it's an issue that I opened inside the Aki.NET project, but it's a comment from a specific user is what I want to go ahead and fixate on for a minute. So the comment I want to go ahead and take a look at is down here. I used benchmark.net in a recent release of Akka.net to go ahead and introduce some performance improvements for a very specific portion of Akka.cluster, which is our networking system inside Akka.net. Well, we have a user down here who went ahead and reported that he was getting high memory usage when using DData. DData is our replication system for Akka.net. So it's what allows us to have multiple writable replicas in memory of the same of the same object. And this DData system relies very heavily on there being multiple sort of exact replicas of the same data structure present in multiple areas of the network, and they can all be merged together again. And we use a versioning tool called a vector clock for being able to keep track of which version changed where inside the system. So this user reported that in a 7-node cluster, I have a 5 megabyte DData file, no other activities happening in the cluster except for internal gossip, and I quickly run out of memory. 512 megabit container with lots of exceptions like this below. And so it looks like we're allocating a lot of memory. This stack trace right here is coming from our serializer, which is responsible for essentially moving bits back and forth between nodes. So the serializer is taking messages that were on the wire, turning them back into data structures that are in memory here. And it looks like in this case, we just happened to run out of memory while we were deserializing a data structure from Lightning DB down here, which is a way we can go ahead and save these special data structures on disk. But the point being is that we want to go ahead and take a look at how much memory are we taking up to go ahead and construct these objects. Why are we using so much memory to do it? And where's that cost really coming from? Now, we know based on this previous issue that I referenced here, this vector clock performance optimization. Vector clock is also used inside DData. It's also used inside Akka.cluster. But if I scroll down, we notice that in .NET, the key value pair .equals method was responsible for a tremendous amount of allocations and a huge amount of latency when comparing different versions of the same structure inside Akka.net. So if we want to go ahead and try to reduce the latency of, let's say, merging lots of different complicated vector shapes together inside Akka.net, the way we can go about doing that is by essentially trying to convert key value pair into a value tuple, which is a newer type that got introduced later after we originally developed these data structures. So benchmark.net was very helpful in being able to go ahead and measure the efficacy of some of these changes that we introduced. So benchmark.net is another open source project. It's a very detailed micro benchmarking library, and it's perfect for these types of use cases. Where we want to go ahead and take a look at trying to improve the performance of, let's say, a data structure or a single method on an object, that type of thing. Macro benchmarks, which are also important. This is where you're benchmarking groups of features together all at once. Benchmark.net doesn't quite give you the level of detail you need for that. Let me rephrase. It gives you too much detail, but doesn't necessarily help you figure out whether or not your changes helped at a macro level or not. So the approach for performance optimization we're going to use here is micro benchmarking. We're going to go ahead and gradually make changes to some of these underlying DData structures in order to try to make them faster, make them allocate less, and try to go ahead and improve their overall performance. So if we take a look here, these are some of the measures that this vector clock benchmark I added just a couple weeks ago to Akka.net did. We can go ahead and see down here that our mean, so basically we're doing 1,000, I think, mutations. So we're doing a vector clock comparison, comparisons where one of the objects is a different age than the other. And you can see these have roughly pretty similar latencies, all these ones right here. And then these latencies down here, where we're basically looking for a not equals, or we're looking for two objects that are much more similar than some of these ones up here, you can see that these comparisons tend to short circuit, so they take a lot less time to perform. And then these comparisons down here, these other not equals, these ones short circuit very quickly. That's why they take 1/20th the time that these do, where I have to perform a full comparison up here. And then if you take a look at the amount of data allocated, you can see that we're down to basically 900 kilobits for comparing 1,000 of these objects. And each one of, well, not 1,000 of these objects. We're doing 1,000 comparisons of an object that has 100 nodes in it. So we're not allocating very much data. If we compare this to where we started at the very beginning, we can see that it took about 100 milliseconds for that 100 size vector clock to be compared 1,000 times. And if I scroll over to the right, we allocated 31 megabytes. So going from 31 megabytes to 900 kilobits is a 2 order of magnitude improvement. So that's the type of performance gain we're looking for. And that might be what we can use to go ahead and help these users right here. So the first thing I want to take a look at is what type of data structure are they working with? And this looks like an OR set. This is short for, if I pull up the Akka.net website here, this is short for, if I go down to distributed data, an observed removed set. So this is a type of hash set that can be merged from multiple writable sources together into sort of one single view further downstream. So let me go ahead and take a look at what sort of benchmarks we have available for this. So this is the source of the Akka.net project itself, and I already have a benchmark.net project configured over here. So it says here that we're going to be building against a .NET Core test version. I believe this is .NET Core 3.1. I could easily change this to say .NET 5. The numbers will probably be better if we're using .NET 5. Each new version of the .NET runtime has had a lot of tremendous performance improvements to the underlying data structures. So that's something we could take a look at here. And then we're bringing in the benchmark.net library. Bringing in, as far as I know, the most recent version of it. And the way our application is structured is we're telling benchmark.net to go ahead and look for all of the benchmarks that are declared inside the currently running assembly. And this will give us a nice little bit of dialogue that I can pull up right here. Let me grab my terminal. I'm going to go to the benchmarks folder, and then I'm going to go to the Akka.benchmarks project. I'm going to do .NET build, C release. All right, this should let us go ahead and compile the latest sources real quick. This will only take just a moment. All right, once that's done, I can go ahead and do .NET run C release right here. And this will go ahead and launch benchmark.net. And this will give us the option to go ahead and choose all the different benchmarks that are currently defined inside this assembly. So we have about 15 of them right now. I could go ahead and put in a number of them if I wanted to run several benchmarks back to back. But typically when I'm working with it, I want to go ahead and just pick one little benchmark at a time. So I'm going to go ahead and quit out of that. Now let's take a look at adding a brand new benchmark for distributed data. So I'm going to go ahead and create a DData folder. I'm also going to go ahead and do benchmark DData or set. I'm also going to go ahead and switch to a new branch to try to improve the performance of our observed remove set. So next, I'm going to go ahead and add a new item. And I'm going to go ahead and create, let's see, I think the naming convention I've been using for these is like OR set benchmarks.cs, I think. Let me double check that. Let's see. Yeah, that looks about right. All right, and next I'm going to go ahead and grab this configuration type from .NET Core. So I'm going to go ahead, not .NET Core, excuse me, benchmark.net. I'm going to go ahead and import all these types here. All right. Now, the next thing I'm going to go ahead and do is I'm going to set some parameters for the types of node size we're going to use, and I might also go ahead and set some parameters for how we go about actually, creating the object that we're going to test. But before I do any of that, I should go ahead and pull up the source for distributed data and take a look at how we would go about actually allocating an OR set in the first place. And the best place for me to look at some of this would probably actually be our unit tests. Let's take a look at that. All right. So looks like we went ahead ahead and we created some keys here, some unique addresses. So we're going to need to do some of this inside our benchmark as well, probably. And then we go ahead and create or set string empty, add some objects to it, and then we can go ahead and perform some different types of comparisons. Okay, well, that sounds good to me. So why don't I go ahead and I'm going to steal some of the data from our previous unit tests here. So let me go ahead and grab these 3 nodes, add that. That looks fine to me. And then, you know what? I should just take it a step further. Do that. Private read only, unique address. That way we can cache these values and reuse them so they won't show up in our benchmark later. We gotta import our address spaces. That's all fine and good. And we'll go ahead and do this for all 3 of the nodes that we might want to use as participants in this little distributed data benchmark we're going to run. Next, I need to probably go ahead and create a baseline observe remove set of some type, and I probably want to add some test data to it as well. The test data is pretty arbitrary. It shouldn't really make much of a difference, but I'm going to go ahead, copy this structure as well, stick this in here. So all of these, values that I'm declaring here are essentially going to be created once for the benchmark and reused over and over again. So they shouldn't have much in the way of a performance impact on anything that we're about to test. So this is looking good to me so far. Next, I should probably go ahead and create some of these little configurable values that we mentioned earlier. So let's go ahead and do this. I am going to, actually, you know what I'd really like to do? We should go ahead and talk a bit about, not the node size necessarily. We should go ahead and talk about, call it transformations. All right, so 10, 100, 250. That sounds good. Next, I need to go ahead and create a global setup. So this is where we go ahead and initialize some of the data that we're going to use for running these benchmarks. So I'll add a benchmark for doing a serialization as well, which is actually where we saw this error show up. But let's go ahead and see how well this observe remove set performs just with doing basic construction for now. So I'm going to go ahead and create or set. We'll go ahead and call this string. We'll call this init, and this will be an empty OR set. So then our init, I'm going to go ahead. Actually, you know what I'm going to do? I'm going to go ahead, not make this read only. These are all meant to be immutable, all these classes, which means that I don't necessarily need to worry about keeping track of changes as the benchmark runs. Every single time we perform, like for instance, if I do this, init dot, let's see, add, I need to go ahead and add an element that belongs to one of these nodes. Let's go ahead and add node 1, and then we'll add user 1. This is actually going to return a new OR set object. So init will be equal to that. So this is the basics of immutability. That's important for an object like a CRDT, conflict-free replicated data type is what this is. It's important for that because that object is designed to be manipulated in parallel in multiple places inside the network or possibly in multiple threads, and all those results get merged back together again. So what we're going to go ahead and do is we're going to go ahead and populate this set with one initial item in it, and then we're going to create a benchmark for doing something really simple. We'll go ahead and add a single new item from a different node to this benchmark, and we'll go ahead and see how quickly those two copies can be merged back together again. So I'll go ahead and call this should merge add from new node. And I've got to go ahead and add an attribute to this to declare a benchmark here, and I believe that is just this one. Yeah, here we go. Let's see. Yeah, I'll go ahead and do that. Now, next thing we're going to go ahead and do is take a look at our OR spec down here, some of the little operations that we did in the past. You can see that we've been doing both adding and removing elements from different nodes, all that sort of stuff. So the first scenario we might want to try is right now our observe remove set only contains one element from one node. What if we add that same element from a second node? How is that going to go ahead and affect the performance versus adding, let's say, a new element from a different node? Well, that's something we can go ahead and benchmark. So I'm going to go in here to my benchmark, and I'm going to say, all right, new OR set equals, and we'll go ahead and say init.add node 1 user 2. This is actually adding a new item. Let's go ahead and do node 2 user 1. So the same item is being added from a different node. This is fun stuff you get to think about. And I'll go ahead and call this C1. And then next thing we can go ahead and try. In fact, you know what I'm going to do? I'm going to get rid of this variable for now because we're not really using it. Next thing we can go ahead and try is, let's see, adding node 1 user 2. Why don't we go ahead and keep it really simple for now. Really simple benchmark. Okay. Should add, let's see, same element from new node. All right. This gives us a really simple benchmark. So far, we're just adding one element to an existing OR set. This should be able to help us figure out, and I believe this is configured to show the memory diagnoser. Let me just double check that real quick. Yes, it is. Perfect. So I'm going to go ahead and run this, and this will give us a little report in Markdown that we can use to diagnose just how expensive the OR set is from a memory consumption point of view. So this new benchmark I just added shows up as item 10 on our set. So I'm going to go ahead and pass that in. And benchmark.net is actually going to go ahead and compile a little program behind the scenes, which is going to go ahead and help us keep track of just, oops, looks like we had a bug there. Object reference is not set to an object setup. Well, that would do it. So I need to go ahead and put orset.empty right here. There we go. Okay, so I had a little programming error in there. Let's give that another try. Okay, we'll go ahead and run that again. Now it's not failing right away, so that's giving me some hope that we did this right. All right, there we go. So one of the things benchmark.net's going to do, and you can see it kind of doing this right now, is it's actually warming up the process behind the scenes of this benchmark is running in order to make sure any just-in-time compilation overhead gets kind of pushed out of the system. This is going to force the CPU to go ahead and cache some of the instructions that are being used inside of here. Now, the first thing that we go ahead and notice is that it took about 5.416 microseconds, that's a millionth of a second, to go ahead and add a brand new item to this observe remove set. And we had a small amount of allocations in Gen 0. But the thing that alarms me most is we allocated 1.9 kilobits in exchange for, and all we're doing is we're adding the same piece of data just from another node. And the node's address and the actual item we're adding are both cached in memory. So they aren't even factored in on here. So that's a little disturbing. So let's go ahead and take a look at should add, new elements from new node. So let's go ahead and give this a try. We're going to go ahead and add node 2 and node from user 1. C2 is going to go ahead and add from node 1. So I'm waiting for Visual Studio to play catch up here. Sorry, it looks like ReSharper is hogging the thread. Give that just a second. Yeah, that doesn't work. I can go to Visual Studio Code. Well, gave that a shot, Visual Studio. Thanks for playing. So I go to akka.benchmarks, and I go to my DData benchmarks I've been creating. I go ahead and say, all right. It looks like Visual Studio actually crashed and is reloading the solution now in another window on my machine. That's kind of funny. I'll go ahead and just shut that down. We'll go ahead and do var c2 equals c1.add. And we'll go ahead and do node 3. Actually, we'll go ahead and do node 1, user 2. And then c3 will be c2.add node 2 user 1. So both nodes are about to get consistent with each other in terms of, let's say, both node 1 and node 2 know about user 1. And then, oops, I got to do one more. C4, C3.add node 2. Actually, this is what I meant right here. There we go. All right, that looks good. Let's go ahead and run the benchmark one more time. So this should help me zero in on what types of performance problems we might actually have with some of our code behind the scenes here. That's going to go ahead and run in the background. This is mostly just jitting overhead. By the way, we're going to see one of these for literally every benchmark that we run. So we're going to rerun the results from this first benchmark again, but then we're also going to run the second benchmark, and they'll both show up in their own separate little markdown reports once this is all done. All right. Now, I'm assuming that these 14, 15 microsecond operations have to be coming from the second benchmark, because this is roughly 3 times the amount of work that this one was. And we saw in our previous benchmark, this took about 5 microseconds or so. That's what I'm assuming. All right. Yep, looks like my assumption was right there. So it took us 15 microseconds to go ahead and add a total of, let's say, 3 elements to that collection. And then that allocated in the process about 5 kilobytes or so. Okay, well, one thing I can go ahead and do is, let's make this a little bit more interesting. I'm going to go ahead and create an arbitrary array of nodes in this case. So we can go ahead and really create a much more flexible benchmark now. And this is where, let me go ahead and say close all other tabs. There we go. Let me go ahead and pull up one of my cluster benchmarks again, just so I can get this back. So we're going to go ahead and make the object sizes a little bit bigger and call this num elements. And the reason why we want to do this, let's see, number of elements, and then we'll go ahead and do public int num nodes. And we'll go ahead and add some params for this as well. I'm going to go ahead and not include 100 elements for now. That just might be a little much. And then for the number of nodes, let's go ahead and say our replication factor can be anywhere from 3 to, let's say, 10, somewhere in that ballpark. So I'm going to go ahead and have us always start with, let's say, a relatively empty set of benchmarks here, a relatively empty set of OR sets. So I'm going to go ahead and create, actually I'll leave that alone for now. I'll go ahead and create a private unique address nodes. We'll create an array, and we'll do private string elements. And then I'll create a little function right here. Private. We'll go ahead and call this unique address. Actually, I guess we can just call it private init. Private void init. Actually, I don't even need that. I can just do that in my setup. Okay. For I in num nodes, and we'll do enumerable dot range 0 num nodes like that. To give us a little for loop I can iterate over. I think I need to add namespace for that. And I can go ahead and say, all right, I'm going to take my little little unique address here. So I'm going to go ahead and grab, let's see, we'll go ahead and do var address. Var, okay, new nodes, new list, unique address. All right, new, let's say, address. And we'll go ahead and start with all these components, then change the port number. So we'll go ahead and say I is our port number. And then, actually, you know what? We'll go ahead and do 2552 plus I for our address. And then we'll go ahead and say our unique address equals new unique address. We'll pass in our address here. And I'll go ahead and say the UID is equal to I. This is how we uniquely identify nodes inside our network. It's all that stuff. Now, next thing we'll go ahead and do is each one of these elements we'll go ahead and add to our list of nodes. So I'll go ahead and do add, and then we'll do unique address. And then at the very end, I'll go ahead and say nodes equals new nodes to array. Bear in mind, nothing that's in our setup here is going to get counted against the actual performance numbers we generate in the benchmark. We're just using this to dynamically generate a range of data, and I can configure how big that data is by specifying these parameters up above here. So that's for num nodes. Then we need to do num elements. So I'll go ahead, do pretty much the same thing. New elements equals new list string. Right. Actually, if I want to be really clever, I can do that. That'll go ahead and pre-allocate all the internal buffers and everything, which we don't really need to do, but it's maybe a good habit to get into. Numerable.range 0, and we'll go ahead and do num elements. All right, so I'm going to go ahead and add to my list of elements whatever this integer value is. We'll just go ahead and stringify it. All right, and then elements equals new elements dot jewelry. All right, so now we have a dynamic range of elements, new elements to array. Let's see, cannot implicitly convert type string to string. Oh, whoops. Let's do that. Okay. All right, we should be in pretty good shape there. I'm going to go ahead and get rid of some of these addresses here. I'll even get rid of init. And then I'll go ahead and say, all right, should, build or set of size. Let's go ahead and do something simple. Let's just go ahead and add equals or set string dot empty. Let's go ahead and just add for each node in our network the first item in our OR set. So we'll go ahead and do for each var I, we'll say node in nodes, init equals init dot add, should add node to OR set. We'll go ahead and add node, and then we'll go ahead and do elements 0. Same element for all nodes. All right. And then down here, we'll go ahead and say, all right, let's see. Should add elements for same node. So we'll go ahead and switch this around here. We'll go ahead and change this to element. Change this to elements. And we'll go ahead and say for nodes 0, we'll go ahead and add this element. All right, so both of these will probably have pretty similar impacts on the performance, but let's just see. What's the cost to adding new nodes versus adding new elements for the same node? What does that look like from an OR set point of view? Let's go ahead and compile this, see what we come up with. All right, let's run that. Oh, let's see. Danthar, are you taking advantage of data store for distributed sharding as example here? Yes, I am. The reason why we're looking at distributed data is because when we were doing some work in Akka.NET 149, we noticed that the vector clock, which is used to version the cluster membership state, was enormously inefficient from a memory point of view. And that's primarily because key value pair dot equals allocates a ton of objects, whereas value tuple doesn't. So we were able to improve the latency and the memory overhead by about 2 orders of magnitude. Another user, after we mentioned that, hey, the distributed data uses the exact same vector clock behind the scenes, we went ahead and said, uh, you know, we should probably fix the performance here. Another user said, yeah, I keep running out of memory inside my application whenever we're using it. So I figured we should go ahead and start benchmarking the data structures themselves. And then next thing I take a look at the version vector, which is the little component that's responsible for versioning these objects as they change over time. So we're just kind of gathering some baseline performance data here. We haven't even started working on trying to improve the data structure. We're just trying to see sort of what the terrain looks like so far. And then we're also going to need to add some benchmarks. In addition to just adding items to the set, we also need to take a look at removing items and potentially, removing nodes from the cluster, all that sort of fun stuff. So we should get our first round of data in just a second. That'll kind of help us figure out whether or not these changes have severely different sort of performance impacts. Now, by the way, the reason why this is running multiple times is I basically defined a testing matrix right here. We're going to do one set with 10 elements with 3 nodes, one set with 25 elements with 3 nodes, one set with 10 nodes and 10 elements, and one set with 10 elements, 10 nodes and 25 elements. So we're going to go ahead and run all these combinations sort of exhaustively here. And we should get a performance report for each one of them once this finishes. All right. So we should be done in probably just a second here. Nope, maybe we have one more set to go. All right, so the results are in. So what have we learned? Well, should add node to OR set when we have 10 elements and 3 nodes. The overhead is about the same as when we're adding just one element. So impact doesn't appear to be that big necessarily when we have, let's say, 10 elements and 3 nodes. Now, adding, elements for the same node when we're doing 10 elements, we're allocating about, 1 kilobit and change each, all right? Well, what happens when we have 25 elements and 3 nodes? Well, the memory overhead for adding 25 elements versus adding 10 elements is identical. So that tells us that the cost per element is probably not that high necessarily. So that's a good thing. That's worth looking at. All right, new subscriber, sweet. So that's one thing we're looking at, is the total amount of memory for, let's say, 10 elements versus 25 is not even measurable. But the difference between, let's say, adding 10 elements to 3 nodes versus, let's say, adding 10 elements for 10 nodes is quite a bit bigger. So we know in this case that let's say the level of volume that's being driven in terms of where a memory consumption is probably highest is probably, let's see, if we take a look down here, 25 elements for the same 3 nodes is 31.56 kilobits, whereas 10 elements of the same node is 10 kilobits. So yeah, so it looks like it's actually, sorry, I got that backwards. Looks like adding the nodes to the OR set is pretty inexpensive. Doesn't really change much for a single element, but adding multiple elements to the OR set per node is what adds this cost here. So we can kind of start to see the values growing behind the scenes. So next thing we should probably go and take a little look at is why don't we go ahead and see what the impact of different operations is. So far, all we've been doing is just adding elements to our observe remove set, but we have a bunch of different operations we can execute against it. So let me pull up the actual code for distributed data here. And that should be cluster, distributed data, and then observe remove set. And then actually what I kind of like looking at to grok really quickly what this code does, even though I've worked on this code base for years. So I like taking a look at the unit tests. So we have the ability to go ahead and add and remove nodes in here. We also have the ability to merge two totally different sets together. So I think it might be worth trying to go ahead and measure the performance of removing elements from the set and merging two distinct versions of these OR sets together. So let me go back to our benchmark here. I'm going to go ahead and create some cached observe remove sets so we don't measure the overhead of trying to create new objects necessarily. So I'm going to create an OR set string called C1 and C1, and I'll go ahead and create C1 and I'll also do, I'll go ahead and do C1 and I'll go ahead and do C2 and I'll even add a C3. And I'll go ahead and say down here that C1 is going to initially start off as OR set string empty. So this could be an initially empty. In fact, I'll make all these empty initially. That'll help just simplify things, so I don't get any null reference exceptions later. All right, that looks good. Now, what I'll go ahead and do is I'll say, has data from all nodes. We'll go ahead and say has additional items from all nodes, and then we'll say has removed items from all nodes. So that way we can go ahead and measure the merging performance of these three structures. So I'll go ahead and say C1 is going to have, for every node in the cluster, we're going to go ahead and add element 0 for this. So C1 will basically be identical to what we produced here. And I'll go ahead and say C1. Now that looks good. Now, next thing we'll go ahead and do is for each of our node in nodes, and I'll go ahead and skip half of the list. So I'll go ahead and say, let's say nodes dot, actually I guess we have a num nodes field. Num nodes divided by 2. Go ahead and skip that. Do a little bit of integer arithmetic to make that into an even, basically not a fraction. So that should be fine. So we'll go ahead and say, all right, for each node and nodes skip, we'll go ahead and say C2 equals, actually, you know what? Let's do this. C2 equals C1. So we're going to go ahead and evolve C2 a little bit. C2 is going to have some changes C1 doesn't have. So I'm going to go ahead and add in half of these nodes. I'm going to go ahead and add, let's see, we'll go ahead and do node, and we'll go ahead and add elements 1. We know we're going to have at least 2 elements in the elements collection. All right. Add some data that C2 doesn't have. And because this is immutable, I need to do this. All right. And then, just to make things extra confusing, I'll go ahead and do nodes.take. We'll go ahead and do just the first half rather than the second half down here. And I'll go ahead and say C3 is equal to C1. And C3, I'm going to go ahead, and for each of these nodes, we're going to go ahead and remove. We'll go ahead and say elements 0. All right, these are our 3 structures, so they should all have slightly different versions of the same content together. Now, what I'm going to go ahead and test should merge in new elements from other nodes. All right, we're going to add this benchmark. And for this benchmark, I'm going to go ahead and do var C4 equals C1 merge, and I'll go ahead and add C2. We're going to go ahead and merge those in. Then I'll add a second benchmark. Should merge in new, let's say removed elements from other nodes. We'll go ahead and do C1.merge C3. And finally, we'll do should merge in, add, and removed elements from other nodes. So we'll go ahead and do C4 equals C1.merge C2, C5 equals C4.merge. Actually, easier way to express this. Merge C3. All right, there we go. Now I'm going to go ahead and compile this again. All right, and then let's see. I think I might be able to even filter these benchmarks so I can skip the first two. So let me go ahead and do, I want to select a few. Why don't I go ahead and do this? I'll go ahead and do filter, and I'll go ahead and say should merge. All right, see if that works. Should merge. Okay, well, let's see what benchmark.net's going to run. Should merge in. Okay, perfect. It's merging in all of our operations from these should merge statements that I defined. So it's running, I think, these three benchmarks right now. So we're able to go ahead and basically filter based on the matching titles. It looks like all that's going through. And this should only take maybe a little bit. Looks like the merge operations are actually pretty fast, which is a little surprising to me. We're going to come up with some more complicated merge operations that we'll do later where we're merging really large items together. Like I mentioned in the slide, one of the things you want to take a look at when you're doing benchmarking is we want to go ahead and take a look at important edge cases. So this user who reported this bug where, distributed data was consuming all the memory in their application probably has an edge case where the object's very large or the contents of that object are changing pretty rapidly. So those are things we're going to need to write some benchmarks for. It'll take a little bit of trial and error to kind of see where we need to look based on some of this benchmark data that we're generating. So let's take a look. Let's see, this should probably be, so we have to do, I think, a total of, based on the little matrix we have here, I think we have to do a total of 6 different iterations. All right, so that should all be going through here pretty quick. 6 iterations per benchmark, so I guess that'll be 18 total since we're running 3, but all of them seem to be going pretty quickly, so this shouldn't take too much longer. While we're at it, one thing that might be worth looking at is the piece of code we're actually going to try to improve the performance on, which is our version vector. Here we go. So we know this class has performance problems, and specifically the area where, based on our experience, we're going to knock out a cluster. We know the area where it has major performance problems is down here, where we're actually going and comparing these key value pairs together. By changing this method to take a value tuple instead of a key value pair, where the syntax is virtually identical, based on our experience working with Akadot Cluster, we know that this should help improve the performance pretty significantly in terms of both memory allocation and CPU. However, the observe remove set and some of these other data structures we're taking a look at, we don't necessarily know what types of operations put the most pressure on keeping track of the deltas beneath the covers here. So you can see that we're creating a new version vector down here, for instance, that type of stuff. Well, in those situations, we want to go ahead and try to establish some performance numbers first, which is what we're doing right now. We want to try to get an idea of what's going to ultimately drive some results in terms of improving the performance of these data structures. What we really want to do is get a better understanding of what's going to reduce the allocations in memory, what's going to help us get a better signal to noise ratio on that type of thing. So let's see where our benchmark's at. Yep, looks like we're still doing observe remove benchmarks. Number of elements 25, number of nodes 3. And which one is this? Okay, so this is the final benchmark, and it looks like we've got maybe one more iteration to go after this. But this is taking about 30 microseconds per operation. Now, bear in mind that these observe remove sets that we're actually running these benchmarks on are already pre-allocated. So all the overhead of constructing the objects has already been done. This is literally just merging of two objects together. The fact that it's taking tens of microseconds to do that, because these are all in-memory objects on a very fast Ryzen development machine, means that we probably have some performance problems underneath here. So that's good. This is the sort of divergent result you actually want to see in a benchmark. So let's see. Danthar, you wrote, I would expect that merge would be more expensive if the difference between the aura sets is bigger, as not in their size, but the contents of the strings objects in there. Yeah, I'm inclined to agree with you. I think the looks like the performance scales a lot more based on the number of elements in the aura set versus the number of nodes that have replicas of it. And so, one thing we're going to probably want to do is experiment with generating much noisier looking OR sets, where the size of the delta, meaning the objects that keep track of how different these objects are, needs to be as big as possible. All right, so here's our table, and if I want to get a pretty markdown representation of this, I can pull up, this is just GitHub for Windows. I can go ahead and pull up our little benchmarking figures right here and say, open this in Visual Studio Code. And let me go ahead and stretch that out just a little bit. All right, I'll go ahead and go full screen for a minute. So what it looks like to me is that the actual memory allocation of, let's say, merging these objects in seems a little high, because bear in mind, we're only talking about like, 10 by 3. So we're talking about maybe a total of 30 deltas. Generating 9K of memory seems a little high. So there's a little bit of memory pressure going on there. One thing we could do to kind of exacerbate this, to make it a lot more obvious where the memory problems are, is I could actually go ahead and run, if I go back to, oops, I had the right window all along. I could actually run this code inside a loop, where I might say, run this 1,000 times. And that would go ahead and push the, that would go ahead and basically push up the numbers you're seeing to much higher orders of magnitude. That is actually helpful because benchmark.net is very good at measuring things very precisely, but there's all sorts of things that can happen inside a managed programming language like C# or F#, where the way memory gets manipulated can be hard to miss when you're not using very much of it, and the number of allocations itself is pretty small. Putting it into a for loop kind of blows that up and makes it easier to go ahead and observe over, let's say, the course of 100 or 1,000 iterations, just how expensive something is. But just even looking at these micro benchmark numbers, I can just tell you, by gut instinct here, taking, let's say, this is half a millisecond, I think. Nope, 500 of these would be half a millisecond. So this is about 1/10 of a millisecond to go ahead and merge these two objects together. That seems like it might be a little expensive to me. So one thing I'm going to go ahead and do for the next round of benchmarks, and I'm probably going to go ahead and run these inside a loop. Danthar, there's a Markdown plugin for VS Code that renders it as an HTML preview screen. There is? All right, well, let me see if I can find that. Let's see, plugins. I think that's it right here. Markdown preview. Markdown preview enhanced. 2 million installs. Seems legit. All right, let's give that a try. Then to go ahead and run this, what do I need to do? Key bindings. Let's see. Control K, Control V, or Control Shift V. All right, let's give that a try. Control Shift V. All right, now we're in business. Preview's built in now. Man, well, I'm kind of a newbie to Visual Studio Code. I've only been using it because my last bit of code that I've been working on is last bit of code I was working on is .NET 5, and it uses all record types, and ReSharper or Visual Studio don't support those very well right now, whereas VS Code has no problem with it. So I've been picking it up, but not quite an expert in it. Okay, so we know that we've got, I think we're pretty sure that we've got some performance problems down here. Now, I have to go ahead and end our stream for today, unfortunately, because I've got to go head to the airport and grab a flight. But thank you very much for following today. This is a lot of fun. I'm hoping to actually get on a consistent schedule and do this more frequently. And so the next time we pick this back up, we'll go ahead and be doing a lot more. We'll be taking a much closer look at how to do actual performance fixes on this code. And we'll probably run some more benchmarks, get some more data, and we'll kind of keep iterating through the process of trying to make this whole system a lot more efficient than it is now. So thanks for your time today, everybody. Really appreciate it. And I'm looking forward to doing this again soon. Thank you very much.